All right, so welcome to the first day of algorithmic game theory, hopefully first of many. So first of all, congratulations finding your way here. I know that's a non-trivial task, but I'm preaching to the choir. You all did it, but good job. Let me start, since there's a lot of you, just by trying to get a sense of like who is in this room. So if it was a small class, I'd go through and ask you to introduce yourself and tell me what your major was, but there's too many of you for that. So let's try like some simple polling. So like, first of all, who here is a nets major? Okay, are you a nets major? Are you a nets major? I just asked if people, no? Okay, good, you didn't miss anything. Let's see, who's computer science? Who's math? Who's economics? Who's something I didn't mention yet? Okay, let's see. Let's go through the people who are raising their hands now who are something I didn't mention yet, and they can all tell me what they are. PPE, what's that? Philosophy, politics, economics. Cool. Now, keep your hands up, please. Systems engineering, cool. And yeah. Physics, awesome. People have put their hands down, but you are still brave enough to keep it up. Physics, nice. Anyone else who previously had their hands up? Physics. Cog-sci. Cool. So it's a diverse group of people. That should be fun. So, okay, so like basically, for every lecture except this lecture, I'm gonna be going through, in the style of a math class, definitions, lemmas, theorems, proofs. This lecture, I'm not gonna do that. This lecture is gonna be, in a couple of parts. The first part is just like boring logistics, like how do I assign grades? Like, should you cheat on your exams? Things like that. Then I'll try to do some, like rah, why should you study algorithmic game theory and be excited about it? And then at the end, we'll try to, maybe see just a little bit of the kinds of things we'll be studying in this class, but not at any level of mathematical detail. Everything today is pictures and rah, but like don't let that mislead you. Starting next class, definitions, theorems, proofs, and that's what the problem sets are going to be like. So to the extent that you've come here not knowing what kind of class this is a math class. Okay, so let's start with the boring stuff, basic parameters. When and where? Well, okay. This message is intended for the people who didn't make it here today, but here and now. And we've got a great team of instructors. So I'm Aaron, I'll be your professor, and we've got a great team of TAs. So we've got sort of PhD student TAs. You can think of these maybe as the head TAs, Natalie and George. Natalie is over there. George is not here at the moment. And we've got a great set of undergrad TAs, Charles, Rohan, and Kevin, and you'll run into all of us. We'll be holding office hours and such. So this, you should take advantage of the great TA team. And okay, so I'll be here lecturing to you twice a week. And by the way, hopefully it'll be sort of like participatory. This is more fun if you ask questions. The way that eventually we take this class and turn it into grades is through problem sets, midterms, exams, and participation. So a little bit less than half of the grade, 45%, is going to come from the problem sets. These are bi-weekly, so every 2 weeks, there's going to be 6 problem sets. I'll ask you to prove things, analyze algorithms. You will do it and submit it on Gradescope. About halfway through the term, we'll have a midterm exam, and at the end, we'll have a final. Those are each worth a quarter of your grade. and the remaining 5% is participation, which either means in class, if I recognize you as someone who's coming to class and raising your hand, that'll do it, or on Slack. So there's a Slack channel for this class. If you were registered for the class as of a couple days ago, you've already been invited to it. If you weren't, send me an email and I'll send you an invite to the Slack channel. Yeah, so in terms of like infrastructure, I don't plan on using Canvas at all. Basically, there's a course website, there's a grade scope, and there's Slack. So the lectures, the notes from the lectures, like for example, these slides are going to be posted on the course website. You can find that on my website. It's also posted in the Slack. Questions and discussion, I'm going to try to do that in Slack. So, if you have a question, ask it in Slack, and I or the TAs will answer it, or even better, like before we get to it, one of your peers will answer it. Yeah, so I'm hoping that the Slack channel will be a easy informal discussion space for us. And for turning in the problem sets and for receiving your exams back, we're going to use Gradescope. Hopefully you've all used Gradescope before, but if not, you should familiarize yourself with it before the first problem set is due. And it just sort of, makes things easy, turned it online. It enforces deadlines without us having to worry about it. It lets you get your grades back with feedback, submit regrade requests, things like that. Yeah, so like, I'm going to try to run this class basically with what I'll call the reasonable person principle. So there are problem sets. They're sort of, when you're working on sort of proof-based problem sets, it's more fun to work together with people, so that's allowed. But everyone should do their own work, which means you should feel free to talk to each other about the problems, but everyone should write down the solutions themselves, and you should write on the top of your assignment who are the people you worked with. Okay, so say you work in a group of 4 people, everyone turns in their own assignments. Everyone in that group lists on their assignment the names of the others, and you're not turning in like verbatim the same thing because you've written up the assignment yourself. You've only sort of discussed the problems with each other. Okay. Flexible late policy. So basically, the intention here is I don't want to deal with a lot of special cases where people send me emails saying, oh, whatever thing came up, can I turn it in a day late? The answer is yes, you can always turn in your assignments late, but there's a sort of smooth sliding scale that will penalize you for it. So 20% off per day late without any questions asked. So if you turned in, if it's due on Tuesday and you turned in on Wednesday, multiply the score by 0.8. Okay, so that's the sort of basic parameters, and then I'm going to get to the rah parts in a moment. But before we do that, are there any questions about sort of the basic functioning of the class? Yeah. We do not. It will be roughly midterm, and I will try to set it soon, but it's not set yet. I'll post it on the website and on the Slack when I know the date. Other questions? Yes. They will probably generally be due on Tuesday. The first problem set's going to go out next class, which is Tuesday, and then every time a problem set goes out, you have 2 weeks to do it. So unless something comes up like a snow day or something, I expect that they will go out on Tuesdays. Good questions so far. Others? Yes. You'll see, I guess. If you're on top of the material, certainly, I don't think you'll need the full 2 weeks. Certainly, if you're not taking any other classes, but.
Will there be office hours by you or the TAs?
There will be, yeah. So we're still getting the time set up, but we'll sort of post that on the website and on Slack. And I think, so there's, I guess, 6 of us. We'll aim to have office hours spread throughout the week. So hopefully you can, at any time, try to find one of us. Good questions. Anything else? Okay. Okay, so let me start maybe by trying to describe what is the high-level distinction between game theory and mechanism design from algorithm design, which is something that if you're coming from a computer science background, maybe you're more used to thinking about. Okay, so at a very high level, if you take a class like 320, like an algorithms class, by way of metaphor, you can sort of think of yourself as designing clockwork. You might be designing something really complicated, but push comes to shove, you are in control of every aspect of the system, right? Like you might be designing some complicated algorithm, maybe it's got, different subroutines, maybe they're doing things that interact with each other in non-obvious ways. The analysis that the algorithm is correct might be complicated and non-obvious, but ultimately, like you are in control of every single moving part. And your goal, the general exercise in a class like 320, is to orchestrate a computation so that it does what you want. Okay. But in the modern design of systems and platforms and apps, that's often not the scenario we're in, where we get to control every single one of the moving parts. Okay, so if you are designing, for example, a dating app or a platform like Uber or Instacart or something, or a social network, there are, of course, algorithm design problems in there. You're designing Twitter, how are you gonna rank the tweets? How are you gonna manage some large distributed database? But there are very important moving parts, the users, that you do not get to control, right? Like you don't get to tell them what to do. You can influence what they might do. You can, through your design of the system, control sort of the kinds of things they can do, their action set. Maybe they can, like things and retweet them and quote tweet them. You can introduce new functionality. You can try to provide different kinds of incentives. If you're Uber, you can, institute surge pricing. But ultimately, like, if your goal, say you're Uber, if one of your goals is to have your drivers sufficiently spread out so that everyone can, at any time of day or night, get a driver to respond to their call within 5 minutes, you can't really just approach that as an algorithm design problem. You can't just write code for where all their cars should go, right? You have to design the incentives, the constraints, the rules of the system that will cause, all of these decentralized agents who are optimizing for their own objective function, that will cause them to globally do the thing you wanted them to do. Okay, so at a really, the 10,000-foot view, that's sort of the distinction between pure algorithm design and mechanism design. In algorithm design, you control all the moving parts. In mechanism design, you do not, right? You're sort of designing what might be the medium, the platform through which a bunch of people, self-interested agents, are going to interact, and you might know something about what they want. Okay, you might know something about their incentives, but you can't directly control them. And the name of the game is to sort of orchestrate the rules, the incentives, the action space, so that the global behavior of the system is what you want. Okay, so that's like the high-level distinction. The flip side of this, right? Like when I talk about this as a design problem, I'm sort of putting the cart in front of the horse. So like the design problem of orchestrating the rules of the system so that the people within the system act so as to further whatever goal you have for them. That's sort of what's called mechanism design, and that's what we're going to study in the second part of the course. But before you can really do that, right, like set up the rules of the game so that people behave in the game in the way that you want, you sort of need like game theory first, like fixing the rules of the game, fixing a particular interaction. Can you actually predict like what it is that's going to happen? Right? Like if you can't even predict, if you have no like way of thinking about what's going to happen in a fixed interaction, then it's kind of hopeless to think about changing the rules to get behavior to move towards whatever it is you want people to do. Okay, so in fact, we're going to study these in the reverse direction that I just mentioned them, but what is the more sensible sort of intellectual progression, which is first we're going to study game theory, which you can think of at a high level as a way of thinking about making predictions about the global behavior of some system from the sort of, that emerges from the micro incentives of different actors within that system. Okay, and once we have some way of thinking about predictions, what we might expect global behavior of some system to look like given a fixed set of rules, okay, then we can go the next step and think about how to design the rules so that the global behavior is maybe what we want. So this will be one of the maybe sort of top level branching points in this class. About half of the class will be sort of about game theory, in which I just tell you what the rules of the game are and we start thinking about making predictions. And then another half of the class will be about mechanism design, when all of a sudden the rules are not given to you. That's the design problem. What are the, how should we design a system to get the behavior that we want? And this comes up all the time. So this slide is probably like a decade old at this point. So like, it would be much more obvious what to put it on the slide now, right? Platforms are everywhere. We've got Uber and Instacart and DoorDash. These are sort of platforms for matching customers and service providers. I guess even a decade ago, Bitcoin was around. When you think about sort of cryptocurrencies, right? Like, what is, why do you have faith that when you are going to try to execute some transaction, it's actually going to execute? Why do you have faith that, the blockchain is immutable, right? These are not things that have to be true. These are sort of emergent properties because people are incentivized to follow, like to get into Bitcoin mining and follow the protocol. Okay, so these are sort of, at their heart, designed systems that cause structural behavior that is useful to emerge from the interaction of a bunch of people that the designer doesn't get to directly control. Okay. Okay, so that was, like high level, rah, a bunch of pictures. I'm going to start to talk just a little bit more precisely about games, not like very precisely, but a little bit more precisely now. But before I do, are there any questions about the slideshow of pictures I've just shown you and the general, like, what I generally claim is the premise of this class and maybe the salient distinction between a class like this that is centered on incentives and like an algorithm design class? Out of curiosity, I should have asked this at the beginning. How many people here have taken like a game theory class before? Okay, so some of you, but the minority. Okay, so we're gonna, if we're gonna try to make like concrete predictions about what people are gonna do in different kinds of scenarios, we're gonna need some precise way of talking about, what is an interaction? What we're gonna call a game? Okay, so when we talk formally in this class about a game, well, what is it? Well, in order for me to formally specify a game to you, there's three things I need to tell you. First, I need to tell you who are the participants, who are the players in the game. Okay. I need to tell you what it is they can do, right? What are the allowable set of actions for each participant? It's the action set, one for each of the players. And I need to tell you what it is they want, what they care about, right? What are their incentives? And the way we formalize that is through payoffs, through a utility function. In general, the way we're going to model games, the way that is sort of standard in game theory, is we will assign players who can choose actions, utility functions that map from a set of actions, not just their own action, but also the actions of all of the other players. So like a vector of actions, one for every player in the game, to a utility, to a payoff, to like a number that sort of is supposed to encode how happy they are with this particular state of the world defined by the action that everyone has chosen. Okay. And this is just some way of concisely encoding relative preferences over different states of the world, right? Like it's okay if like you don't find yourself thinking every day about like your utility function, right? Like it's okay if you can't answer like a numeric valued question. What is your like utility for, having 6 homeworks in this class instead of 5? You should think of the utility function, the payoffs we assign to different states of the game as some concise way of encoding just relative preferences over different states of the world. Okay. So, like in general, if you've taken a game theory class in an economics department, you've probably come across a lot of like 2-player games, things like Prisoner's Dilemma that I'll mention briefly later in the slides. And generally in this class, we're not going to think about like 2-player games, which aren't, they don't come up that often. They're not like super useful. We'll sort of be thinking of much larger games, like N-player games. But let me show you a 2-player game for now, because in a 2-player game, it's sort of, there's a sort of standard, simple way to like visualize these 3 things. Who are the players? What are the actions? What are the payoffs? Okay, so here's like the standard way of writing down a 2-player game. It's with a matrix, a game matrix. And the idea is one of the players, often called the row player, gets to choose the rows. Okay, so like the row player has 3 actions here, top, middle, and bottom. And the other player, the column player, gets to choose the columns, left, middle, or right. Okay, so the dimension of the matrix specifies like the action set for the player. And then once we pick a pair of actions like middle, left, that points us towards like a particular entry in this matrix, and contained there are 2 numbers, which are the payoffs for the 2 agents. Okay, so like the meaning of 1 minus 1 here is that the utility that the row player has for choosing the middle action, if the column player has chosen the left action, is 1. And similarly, the utility for the column player is -1. And it doesn't matter so much, I could like multiply all of these numbers by 10 and it would be the same game, right? The actual like numbers don't matter. What matters is that these are encoding relative preferences over states. I prefer, if I'm the row player, to be here than I do to be here or here. Okay. And this particular game is one that you might have seen before, right? It's like rock, paper, scissors. This is a very good 2-player game if you want to play a 2-player game. If you've sort of played it before, you'll recognize maybe these payoffs. Rock beats scissors, scissors beats paper, and paper for some reason beats rock. And if we both pick the same thing, right? Rock, rock, or paper, paper, or scissors, scissors, it's a tie. Okay, so we'll like encode that with payoff 0. What I would really like is to win. I'd like to pick rock when you pick scissors, because my rock will presumably smash your scissors, and I will prefer that to a tie. That's why I have payoff 1. You have payoff -1. You don't like when your scissors are smashed. But I would be unhappy if you picked paper, which would shield my rock from view and thereby win. Okay, so that's sort of how you can write down a two-player game. And one of the first things we're going to have to grapple with in this class, right? Like, for a two-player game, this is a very natural way of writing things down. You can like look at it. There's like some numbers. It's a small object. It makes sense. But one of the things we're going to quickly have to grapple with in this class is just sort of like the cognitive load, like the computational complexity of even like forget playing a game, even just like understanding the rules of a game, encoding a game that has more than two players, right? Because think about this: if we had like 3 players, I guess you could have sort of a 3-dimensional cube here, like a 3 tensor, and if we had 4 players, okay, now it's like a 4-dimensional like hypercube, and like in general, the number of numbers I would need to write down to encode an n-player game, if I were going to try to encode it like this, would grow exponentially with n. Okay, so this will be like one of the first things we sort of need to grapple with as we start trying to think about large games. Like it doesn't even make sense to think about arbitrary large games defined like this. There's not enough structure there. So we're going to have to think about classes of games that we can encode in some more intelligent way that have structure, which makes sense, right? Like things that human beings can actually play, interactions that human beings can actually deal with. Like they can't possibly be sort of arbitrary, unstructured interactions in this form. You couldn't even like, you couldn't even store in your brain like, the information you would need to like understand an arbitrary n-player game if I tried to encode it like this. So we're gonna very quickly stop thinking about games that are sort of encoded in this like arbitrary form and start thinking about games that have a lot more structure. That's sort of necessary to think about large games. Okay. So we have a game. We're going to want to start thinking about whether we can predict outcomes or whether we even have like a coherent like way of thinking about that, right? Like, in general, even if I tell you that players prefer high payoff to low payoff states, like, what are they going to do? It's not clear a priori, right? Because of course, if everyone else tells me what they're going to do, then maybe I can figure out what I should do to get the highest payoff state of the game. But if I don't already know what everyone else is going to do, then the thing that I should do depends on what other people are going to do, and the thing that other people are going to do is going to depend on what I should do. And it's this kind of circularity that makes thinking about how to make predictions in a strategic interaction complicated. And so, like, that's the first thing we need to start thinking about. Like, what does it mean? Like, how should we think about predictions if everyone plays rationally? What does it mean that people play rationally? And how robust are those predictions going to be if maybe like not everyone plays rationally, right? Like, we want to make assumptions that, in general are true, but hopefully our predictions aren't so brittle that they entirely fall apart if we haven't correctly captured, what everyone's going to do. And so let's start, let's think very briefly about sort of a stylized game that has a little bit more structure, a game that we can sort of think, an n-player game that we can think about without having to write down like exponentially in n many numbers. Okay, this is related to a family of games that we'll think of in some depth over the next few lectures. Okay, so rather than defining it formally now, don't worry, we'll have plenty of formalism around this class of games, over the coming weeks. Let me just like show you a picture and like describe it to you. Okay, so first of all, the premise of this game is that it's modeling something like traffic routing. Okay, so think about your morning commute. Probably makes more sense if you weren't college students living like in dormitories, but suppose you wake up every day and you get in your car and you drive to work. Maybe you live in some suburb, town A, you need to go to town B, and you've got choices. There's not just one route between point A and point B. Like there's a whole road network of greater Philadelphia. You can choose how you can drive. And the thing you would like to do, your like utility function in this scenario, is you would like to get from point A to point B as quickly as possible. Okay, so you'd like to minimize your travel time. And this is a strategic interaction. It's a game, because your travel time depends not just on the route you take. I mean, of course, it depends on the route you take. If you take like a super long route, it's going to take you forever. But it also depends on the routes that everyone else takes, because how long it takes you to traverse some stretch of road depends on how much traffic is on that road, which depends on how many other people decided to drive on that road. Okay, so this is a good example of a very large scale strategic interaction. Like, we wouldn't want to think about this as like a, n by n by n by n matrix. Okay. Now, in general, like road networks are big, and the function mapping how many people are driving on a road at some particular time to the travel time on that road might be complicated. But let's like squint and pretend that the road network is very simple. In particular, like, you live in town A, you want to get to town B, and there's only two ways to do it. Your action set actually only involves choosing between two routes, this upper route and this lower route. Okay. And actually, like, it's not just you. There's 100 people who are driving between town A and town B at the same time. Okay. Now, so everyone's deciding whether to take the upper route or the lower route. Now, note the edges on this graph have annotations. So what do those annotations mean? Well, the edges on this route are like functions mapping the number of people who are driving on each of these road segments to like the length of time it will take to traverse that road segment. Okay, so when this road segment says that the commute time is x over 100 hours, that means that if there are x people taking this road segment, it will take you x over 100 hours to get from here to here. Okay, so if it's just you, there's only one person on here, you'll get from here to here in 1 over 100 hours, just a fraction of a minute. But if 50 people are doing it, it'll take you half an hour. If all 100 people are doing it, it's going to take you a full hour. Okay, so that's how these road segments work. These road segments here that are annotated, there's no x here, it just says 1 hour. These are that's a constant function. No matter how many people are driving on that road, it's going to take an hour. Okay, so I guess it's like hard to imagine what this might look like as a physical road network, but maybe imagine that these bold lines are sort of direct, but very narrow country roads. Like, if it was just you, it would be real quick. But like, if you try to get 100 people driving on this country road, it's going to be like gridlock, and it's going to take you forever. On the other hand, we've also got these like superhighways. They've got like 100 lanes of traffic. It doesn't matter how many people decide to drive on this road, even if all 100 of them do, basically everyone gets their own lane. So they doesn't really affect traffic, but these roads don't go directly to where you want. They go way out of the way. So whether it's just you or whether it's all 100 of you, traversing one of these big out of the way superhighways takes like a whole hour. Okay, so don't worry too much about what the geography of this road network might look like. Let's just sort of think about this as a game. By the way, even though I haven't drawn for you a matrix and we haven't been too precise about this, like, this is defining, if I wrote down the definitions, we would have defined precisely a 100-person game. There's 100 players, they each have 2 actions, and the annotations on this road network give us a concise way to map the 2 to the 100 choices that each of these 100 agents might make, right? Because each of the 100 agents has 2 choices to make. So there's 2 to the 100 different states of the game. This gives us a concise way to map each of those 2 to the 100 states of the game to a payoff for each of the players. Okay, is that clear? So we can, once everyone makes their choices, I know how many people are taking the path I'm taking. I can read off what is my commute time. Okay. So, suppose this is the road network. People are every morning driving from town A to town B, so they're used to this. They're good at it. What do you expect the traffic pattern might look like? Yes. Yeah. So like you might expect that half of the people go up and half of the people go down. And why is that intuitive? Like what made you say that? Exactly. Like anything other than this would be leaving, time and money on the table, right? Like if everyone was taking the above route, right, everyone would be experiencing 2 hours delay. And it would be sort of there for the taking that someone could think to themselves, well, if I take like the below route, it's just going to take me like a fraction of, above an hour. I could reduce my 2-hour commute basically to a 1-hour commute. So I should switch to the below route. Everyone taking the above route is not a stable situation because everyone has this very strong concrete incentive to change what they're doing. Similarly, if everyone was taking the below route, and if you think about it, anything that's not balanced will give someone an incentive to change what they're doing, whereas this traffic pattern is in equilibrium in the sense that we sort of expect it to be stable. There's no reason for any of these drivers to change their commute because doing so is not to their advantage. In fact, it'll slightly increase their commute if they change. Question in the back. Yeah, so this is something we'll talk about in this class, which is like information, like what do people know? And this is sort of why I sort of said at the beginning that maybe that we should think of this maybe as like a commute that people do every day. So you're right, like, implicit in this is, like, how do I know what everyone else is going to do? Maybe just like by chance, like we all miscoordinate and go up. But like, assuming that we're doing this over and over again, and maybe I can occasionally experiment, if it's consistently the case that I can get there quicker by taking the lower route than the upper route, I'll eventually figure it out. By the way, this is exactly the kind of thing that apps like Google Maps make easier. But like back in the old days when you maybe had to rely on out-of-date radio broadcasts giving you a rough idea of what traffic is like, with Google Maps, like you now have a very precise picture, not of course of the individual decisions of every other person in your city, but of the sort of concise piece of information which is relevant to you, which is what is the current congestion on each of these roads. Other questions? Okay. Okay, so this is a very simple example of what we'll study in some depth called this is a Nash equilibrium of this game, but it's sort of intuitive. This is a state of the game that is in equilibrium in that nobody has any incentive to switch. And if we were in any other state of the game, they would have very concrete incentive to move closer to the state of the game. Okay, so not only is this an equilibrium, this is the kind of equilibrium that you can imagine actually reaching through some kind of natural dynamics, and this is something that we'll study. But if we're not at this equilibrium, then people have incentive to change their action in a way that gets you closer to this equilibrium. And so you can imagine that if we just let people every once in a while change what they're doing to a better action, like not only is this like a stable state of the game, but that there's like a very concrete natural dynamics that if we just let it play out will lead to this. Okay, so in this Nash equilibrium, which happens to be in this example, like the unique Nash equilibrium in this game, the commute time, the delay is 1.5 hours. Okay, everyone takes, like whether I take the upper or the lower route, it takes me half an hour to go along this first road segment because there's 50 out of 100 people on here, and an hour to go along the second, and everyone has a commute of an hour and a half. Okay, in this case, pressing buttons in my pocket. Turn various parts of my phone back on and put it here. Okay, so in this case, the equilibrium outcome is actually also like the optimal outcome. Like if you were designing, if you were in 320 and someone said to you, okay, like these are not people, these are widgets, you need to design the best path for them to take to minimize average, commute time, this is also the solution you would find to that optimization problem. Here, like the equilibrium solution actually does minimize average travel time. But things can behave differently in games. So suppose we elect a new governor who looks at this road network and says, this is terrible. We've got tons of people going from point A to point B, but there's no good way to do it. It's we've got these extremely expensive superhighways, but they don't go right there. They go way out of the way. The only roads going anything directly are super narrow, and they're not connected to each other. So suppose the governor says, okay, he ran on a platform of infrastructure, and so he builds this missing connector that connects these sort of direct routes, okay, with again a superhighway. Maybe these routes were actually sort of, now you can try harder to imagine how this might be embedded in a map, but maybe these routes were actually very close to each other, just not connected. So when I build this connector, now I can actually get from here to here in no time at all. Okay, 0 commute time. Now, if there was nobody else on the road, right, this would be great. If there was nobody else on the road, then before I couldn't get from point A to point B in under an hour, right? It would take me an hour and a bit, because this link takes an hour. This one, even if I'm the only one on the road, takes some tiny amount of time. And all of a sudden, if I'm doing this on Christmas morning, nobody else is on the road. Now, I can get from point A to point B along this zigzag path that takes, a 50th of an hour, right? 2 over 100. So, less than 2 minutes. So this is a huge improvement if I'm the only one on the road. Okay. Okay, but then, okay, so that was great on Christmas morning, but then, the semester starts again. All 100 people need to get to work once more. What is the traffic going to look like on the network now? Yeah, so the claim is that if this is what the road network looks like, remember, this is just an improved version of the old road network. We didn't make any roads worse. We didn't take any roads away. We added a road. If this is what the road network looks like, then now we should expect everyone to take this zigzag path, right? And if they do that, well, the roads get really congested. This takes an hour. This takes an hour. And before I added this road, people's commute was only an hour and a half. But now I've added this road, and all of a sudden everyone's commute is 2 hours, right? And why is this happening? Well, again, suppose they weren't doing that, right? Suppose we were at the old equilibrium. Suppose half of the people were taking the upper route and half of the people were taking the lower route. Well, okay, everyone would have a commute time of an hour and a half, but they would be leaving time and money on the table. Someone could think to himself, okay, well, why don't I take this zigzag path? And if at the moment only half of the people are taking the upper and lower route, this road only takes half an hour. So rather than taking an hour and a half, I could take the zigzag path and cut my commute time down to an hour. Okay, and if you sort of think about it, if not everyone is taking the zigzag path, then there's always some gain to switching to the zigzag path. Because, at this point, if I'm sitting here, I can think to myself, well, okay, I could drive along the out-of-the-way superhighway. That'll definitely take an hour. Or I could go down here and I could drive along this route, which will take at most an hour, but might take less. Right? So if in any other state of the game, other than this, someone has a direct incentive to switch to this path. Okay, but when everyone does that, everyone takes 2 hours now when the previous equilibrium was only an hour and a half. And this is, right, so this is now the unique Nash equilibrium, and the delay is 2 hours. And this is something that doesn't happen in optimization. Right? If this was an algorithms class and we were saying, okay, come up with an algorithm to route packets, route widgets, whatever, in a way that's going to minimize average congestion, average commute time, then increasing the number of options I have, like augmenting the network with more routes, could never make the solution worse, because I always have the option of doing whatever was optimal before, right? Ignoring the new stuff and continuing to do what I had been doing, right? Like adding routes can only help if what we're doing is optimizing. But one of the things that makes strategic interactions, that makes game theory different, is that that is no longer the case, right? Like you can only increase the amount of, the number of options people have, and yet make the outcome worse. So yes, so this is sort of a phenomena that just doesn't arise in optimization, that arises only when you start thinking about game theoretic interactions. This particular one is called Braess paradox. Braess was a traffic engineer. Okay. So like, if I look at this right-hand side network where the equilibrium is all of a sudden bad, it's this 2-hour equilibrium, the old solution is still there, right? Like if I could tell each of the 100 people what to do, right? If I could remotely lock their doors and turn on their self-driving cars and like force them to go along the paths I wanted them to go to, I could still have half of them go up and half of them go down. If I get to tell everyone what to do, I could still get the commute time down to 1.5 hours, right? Like the commute time's 1 hour only because I can't do that, because people are free to optimize for themselves. And so like more generally in a system, you can ask, like how much might performance of the system be hurt because I can't just, because it's a game theory problem and not an algorithm design problem, because I can't just tell everybody what to do, right? And in general, the measure of how much worse things can be because people are optimizing for themselves has the evocative name of the price of anarchy. It is the ratio of the performance of the system in the worst Nash equilibrium, like the worst things can be in a stable solution when people get to optimize for themselves, compared to the best solution that might not be stable, right? The thing that you would pick if you had sort of the power of a benevolent dictator or a typical algorithm designer to tell all the moving parts exactly what they should be doing. Right, so in this case, right, like this ratio is 4/3, because the worst Nash equilibrium here, in fact, the only Nash equilibrium, has an average congestion time of 2 hours. But like if we got to tell everyone where to go, we could get people to have an average congestion time of 1.5 hours. And so 2 over 1.5 is 4/3. And more generally, you could ask the question for different games, like how bad is the price of anarchy, right? Like even in like routing games, like maybe I could like come up with like a more, like maybe I could come up with an even worse example. And maybe an example where the price of anarchy was 10 or 100 or 1,000,000, right? Maybe if I'm clever enough at coming up with road networks, the price of anarchy, maybe I could drive it arbitrarily high. But it turns out that's not the case, at least if we restrict ourselves to linear functions on the edges, mapping congestion to delay, 4/3 is the worst case. Okay, so that's the kind of analysis you can do for a general class of games, right? This is the kind of thing we'll see in this class, but you can say, okay, here's a class of routing games, not just one routing game. A routing game is maybe defined by an arbitrary graph, an arbitrary set of players who might each have a source and a destination, an arbitrary set of functions mapping the number of people on each road to congestion. And I could ask, in the worst case, over any game of that sort, like what is the price of anarchy? How badly astray can I be led by individual selfish optimization compared to global optimization? And you can prove that in some games it's not so bad. In games like this, it's 4/3. And in others, maybe it is. That's one of the kinds of things we'll think about in this class. Question?
Then there's an incentive to switch to the zigzag path. Would we also have to ask that if everyone's taking the zigzag path, then there's no incentive to switch to the up or down path?
So yes, so I guess like when we're arguing that nothing other than the zigzag path is an equilibrium. We're arguing that if you're not on the zigzag path, you have incentive to switch to it, or at least to something else. When we're arguing that the zigzag path is an equilibrium, we sort of want to say, okay, if everyone's taking the zigzag path, nobody has any reason to deviate. And in this case, that's true, because if everyone's taking the zigzag path, their commute time is 2 hours. But what else are you going to do? You know, if you take the upper or lower path, it'll still be 2 hours. Yeah.
You know, Google Maps changes the way they route, like left side or right side, depending on how many people are active. If they have that many people active, they can sort of control.
So Google Maps, as far as I know, greedily optimizes for each user. Sort of says, okay, given what I know and can predict about traffic conditions, here's the best thing you can do personally to minimize your travel time without trying to think about social welfare, right? So Google Maps is sort of acting as a tool to drive people towards equilibrium by helping them optimize individually, as far as I know. That's a good question. It's an interesting thing to think about. I don't know of anything that tries to do it. For various reasons, it's a difficult thing to do. Yeah, maybe we'll talk about that at some point.
Like one person taking the bottom out on 99.
Say that again. Yeah, like here, there might be like sort of due to like discretization error, there might be alternative equilibria where like one person is doing something other than the squiggly route. If I sort of took the limit as x went to sort of n went to infinity, where sort of everyone was controlling just like an infinitesimal amount of traffic, then this would be the unique equilibrium. But you're right that since everyone in this example controls 1/100th of the traffic, I think if one person was deviating to something else, it would also be an equilibrium. Okay, so we can sort of try to think about, you know, we can think thoughts like this, and we'll start thinking them in sort of more precise ways to try to predict what collective behavior might be given the incentives in a system, right? Try to make predictions. We look at a road network like this and we say, okay, half up, half down. Look at a road network like this and say everyone sort of squiggly, right? Predictions not just about like traffic patterns, but about like commute time, 1.5 hours versus 2 hours. And then like we can also think about changing the rules of the game to encourage outcomes that we like. So for example, right, like, you know, the way I presented this was originally the road network, and then, you know, some dumb governor added a road and made things worse. But you can tell the story in the reverse direction as well, right? Maybe this is the road network. Traffic sucks. We don't have the money to build new roads, widen highways. But actually, like in this case, you can like substantially improve traffic by like closing off a road, which is very cheap, right? Like, you know, get rid of this road and all of a sudden you've made things better. Okay, so you can start thinking about changing the rules of the game to improve system performance. We'll think about this quite a lot also in the sort of context of auctions, right? So suppose, you know, everyone in this class gets jealous of my awesome Pixel 4, and I say, okay, you know, I take pity on you. Someone can have this awesome phone. I want to give it to the person who wants it the most. And I say, okay, you know, everyone just tell me an integer that represents how much you want it. And whoever tells me the biggest integer, I'll assume wants it the most, and I'll give it to that person. If these are the rules of the game, will I end up giving my phone to the person who wants it the most? Probably not, right? I'll end up giving my phone to the person who's the best at coming up with big integers, and there's no particular reason to think that's the same as the person who wants it the most. And so I could start to say, okay, well, you know, the integer you tell me is a dollar amount, and I'll give it to the person who names the biggest integer, but then I'll make them pay me that amount of money, which is at least a disincentive to, trying to invent arbitrarily large integers. But if you think about it, also like does not incentivize you to tell me your actual value for the phone, right? Because if you tell me your actual value to the phone for the phone and you win, then you get the phone. But say it was worth $500 to you, you get the phone, but then you have to pay me $500, and so you've sort of you haven't gained anything. It was worth $500 to you. You have the phone, but you don't have $500. And so if the like maybe nobody else valued the phone at more than like $100, right? You sort of would regret if you had told me you valued it at $500, not having said $101. You still would have won the phone, but you wouldn't have had to pay as much, right? So if I said, okay, like whoever gives me the highest dollar amount gets the phone and has to pay that amount. Okay, now you're not inventing arbitrarily large integers, but also you're not telling me what your real value for the phone is. And it's hard to think about what you should tell me. And it might well be that the phone does not go to the person who wants it the most. Okay, so like there's a simple solution to this problem, and we'll think about that in quite a bit of generality later in the class. Okay, now this is an algorithmic game theory class, not just a game theory class. So sort of central to the stories we tell in this class will be computation. So we want, we don't want to just sort of say, okay, Nash equilibria are these stable points. Our predictions are gonna be that people play Nash equilibria. Like maybe, right, like remember even in a game where everyone has only 2 actions, if there's 100 players, there's 2 to the 100 different game play profiles. And really many of these games are much larger than that. Think about driving in Philadelphia. Philadelphia has 1.5 million people. If there's no way to like find an equilibrium except through some kind of exhaustive search, it's not really going to be like a computationally plausible prediction. So we're going to try to like think about ways to make predictions that are computationally plausible, by which I mean, not only should there be like an efficient algorithm for finding the equilibria that we predict will be the outcome of these interactions, but like it shouldn't be like a centralized algorithm that I run on my laptop. It should be like some dynamic, some simple, plausible way in which people themselves might be optimizing that will lead global behavior to these equilibria that will constitute our predictions, right? If there's a simple dynamic that people can play that leads to the states that we predict are going to be the outcomes, that will make the outcomes that'll make the predictions that much more plausible. And so that's something that will be sort of central to our study. Similarly, when we start designing auctions, okay, like if I'm just trying to give my phone to the person who values it the most, maybe that's a pretty simple computational problem. Everyone tells me a number, I find the max. But as we start thinking about more complicated auctions, maybe I'm auctioning off radio spectrum across the United States, and there's feasibility constraints. I can't sell 2 people who are, whose transmitters are close enough to interfere with each other the same piece of radio spectrum. And so like the set of feasible allocations is very complex. It might be that things like, look at the bids and implement the socially optimal solution are easier said than done. That might be a computationally hard problem. And so if we can't do that, how does that limit our design choices when we start thinking about mechanism design? Similarly, someone already asked, about information, like how do we know what everyone else is doing? When we start thinking about like computationally plausible dynamics, ways in which people might play games, ideally it will not require that you know in great detail what all of the other 1.5 million people in Philadelphia are doing today, what like decisions they've made on the road, right? That's not information theoretically plausible. So we're going to want the kinds of dynamics we study, the kinds of interactions we study, to require only like limited plausible amounts of information. Okay, now in some games, equilibrium predictions will be more plausible than in other games. Okay, some games are sort of simple and some games are more complicated. So here's one of these toy, game theory 101 kind of games that if you probably heard about if you haven't like studied in detail, called Prisoner's Dilemma. And I claim that this is a game in which it's pretty easy to figure out what to do and what will happen. And let me like pause for the obvious caveat, because when I say it's easy to predict what will happen in this game, I do not mean that this game is a good model for the actual incentives that actual prisoners might face. I'll tell you the usual story, but like obviously this is a bad model for that, right? So that the claim is very much not that if I study this like 2x2 matrix here, that all of a sudden I will have some kind of insight into the criminal mind and will be able to like, do great things in criminal justice. But that's not a fault of equilibrium prediction. That is a problem with modeling. I would have tried to model some complicated thing with something that is obviously not up to the task. On the other hand, like, right, so I'm going to tell you the usual like story, but the story is just window dressing. Like the game is the numbers in here, and you can have people play this game in a lab where you just tell them the rules of the game. It's on like a note card, and it involves paying people, and so they're actually playing this game. They're not actually prisoners, and equilibrium predictions are pretty good. Okay, so let me tell you the usual story, just for fun. Obviously, this is not a model of that, but yeah, okay. Say we've there's two people who have robbed a bank. Like we know they did it. So we captured them. We arrested them, but actually we don't have like great evidence that's going to stand up in court. Okay, like there was no video footage. They didn't leave any fingerprints. We know it's these guys, but like the case is not going to go through. And so what we need to get one of them to confess to it and help us in the trial for the other guy. Okay, so we put these guys in two separate rooms and we say, okay, you can stay silent, you can say you didn't do it, or you can testify against your partner. That'll help us lock him up. And here's like what's going to happen, and both of them know that this is what's going to happen. If they both stay silent, we won't get them for bank robbery, but we'll find something, tax evasion, and they'll both go to jail for some small amount of time, say 5 years. If they both flip, if they both testify, okay, now we've got them both, but they're cooperating, and so even though maybe we could have put them in jail for 50 years, because they're cooperating, they'll end up getting only 40 years. And maybe the more interesting cases are when I decide to testify and you don't. If I decide to testify and you don't, then they've got a great case against you. You go to jail for the full 50 years, you weren't cooperating, and I get a little bit of time off for cooperation for my tax evasion charge. I only go to jail for 3 years, and vice versa. Okay, so, okay. So obviously this is like not capturing all sorts of things, like I'm not worried about what your friends are going to do to me if I testify against you, so on and so forth. But like, suppose this is the game, right? Like, don't fight the hypothetical. What should I do? So like in general, the tricky thing in game theory, thinking about what should I do, is that it usually depends on what you're going to do. Like, what is the best thing for me to do usually depends on what action you're going to play, and I don't know what that is necessarily. That's what makes it hard to reason about, strategic interactions. But in this case, I don't have that problem. In this case, it's clear what I should do, no matter what you do, right? Like you can like go through it case by case. Like maybe you're going to stay silent, in which case, well, if I stay silent, I go to jail for 5 years. If I testify, I go to jail for 3 years. 3 is smaller than 5, so I testify. Maybe you're going to testify, in which case, if I stay silent, I go to jail for 50 years. If I testify, I go to jail for 40 years. 40 is less than 50, so I testify. And so I might not have an opinion on whether you're going to stay silent or testify, which in general would be a problem when I'm trying to figure out what I should do. But in this case, it's not. in this case, no matter what you're going to do, even if I don't have a theory of mind for you, I have no idea what you're going to do, I have what's called a dominant strategy. Like no matter what you do, there's a single action that is the right choice for me. If what I'm trying to do is, minimize my time in jail. Okay, same for you. So the sort of prediction here, the Nash equilibrium, and in this case, it's actually what's called a dominant strategy equilibrium, is that both people will testify and they'll both go to jail for 40 years. And like, why do people mention prisoner's dilemma? It's not like a good way to think about actual like criminal justice. It's to make the following point. In terms of like social welfare of the prisoners, this is the worst possible outcome. This is like 80 years of cumulative jail time. This is like the longest amount of cumulative jail time of all of the 4 possible outcomes here. Right? The best of them was only 10 years of cumulative jail time. And the diagonal ones were only 53 years. Right? But like somehow like if people are just optimizing for themselves without the ability to coordinate, we saw examples of the routing game in which here, actually you get the socially optimal solution when everyone's optimizing their individual utility function. Here it's the opposite. You get the absolute worst outcome for the players when people optimize for themselves, right? So that can happen too, right? Things can be sort of, right, and it would be the same game if I made these numbers much bigger. So like, it can be that things are arbitrarily worse in equilibrium compared to the optimal solution. Okay, so here it's sort of like obvious how to play the game. That's not always true. Sometimes, you have to think harder about what your opponents might do. So here's another game called Guess 2/3 the Average that we will actually play over the weekend. Okay, so this is no longer a 2-player game, it's a K-player game. Here K is going to be around 60 because it's you guys. And here's how it works. Each player is going to pick a number between 0 and 100. It doesn't have to be an integer. You can pick like whatever wacky number you want. It's just got to be between 0 and 100, and you have to be able to type it into a Google form. Okay, so all of you pick a number between 0 and 100. At some point before Tuesday, what I do is I compute the average of these numbers. And then I compute 2/3 the average of these numbers. And I find the guess that is closest to 2/3 of this average. Okay, one of you will have submitted that guess. Okay, whichever one of you submitted the guess that is closest to 2/3 the average will get $5, right? So I will actually give this person $5 on Tuesday. Everyone else will get nothing. Okay, so I want you to think about this game for a little bit. Maybe think about what does it mean to play rationally? Think about what should happen if everyone plays rationally. And maybe like look around the room, like look at people's faces now. Maybe you know some of them. Think about how rational are these other people in the room. Maybe some of them are rational, but maybe not everyone. And then enter your number. There's a Google form. You don't have to memorize this URL. The slides are on the class website, and I'll put this in the Slack as well. And maybe like before Monday, let's say, enter your number, and that way before class on Tuesday, I'll know who the winner is. Okay. Oh, yes. Yes. So your goal is to win the $5, nothing else. So your goal is to be this person, J, whose guess is closest to 2/3 the average of all of the guesses. So maybe I didn't understand the question. Did I answer it? Okay. Yeah, is the game clear? Other questions about it? Okay. Okay, and so like there's one other thing I want you to do before next class, just to like get in the mindset of thinking about strategic interactions with a bunch of players, like thinking, right? Because you sort of have to start thinking like, okay, you know, not just what am I going to do, but like, what do you think I'm going to do? And what do I think you think I'm going to do? And what do you think I think you think I think you're going to do? Things like that. And so here is like a classic riddle, not riddle, you know, puzzle, something. And if you've heard it before, like, shut up and don't ruin it for everyone else. But if you haven't heard it before, I'm going to tell it to you now. I'm not going to tell you the answer. And the homework assignment is to discuss this on Slack. What do you think the answer is? And again, if you know the answer already, like, don't be a jerk, don't ruin it. Okay, so here it is. I'll call it the parable of the islanders. And so like there's this isolated island, and on it live 100 logicians living, of course, in isolation. When I say they're living in isolation, I mean from the outside world. They're actually quite a social bunch. They have brunch together every morning. Okay, so they're not isolated from each other. They're great friends, but they don't have any contact with the outside world. And because they've been living, you know, basically in isolation for a zillion years, they've developed an unusual culture. And in particular, they've got this like weird thing where if any islander can deduce that she has blue eyes, then like that's a terrible shame, and she has to like immediately, like that night, leave the island. However she can do it, like swim, build a boat, like whatever, just has to like get out of there. Can't come to brunch anymore. Okay. But like these people are not monsters. Because it's like, because of the consequences of learning that you have blue eyes, you also, like, if you see someone has blue eyes, you might know they have blue eyes, but you're not going to tell them, right? You're not a monster, like you're friends with everyone here. So it's a huge faux pas to tell someone that they have blue eyes. You're not going to do it. And like another quirk is that probably because of all the inbreeding on this island, every single person on this island has blue eyes. Okay, they all do, right? And there's no, you know, they haven't invented like mirror technology. There's no mirrors on this island. The water's murky, so nobody can like look at their own eye color. And so even though they might have, everyone can like look out every morning at brunch and see 99 pairs of blue eyes staring back at them, right? So like they might have suspicions about their eye color, right? But they don't know for sure. And so since nobody tells them their eye color, they've all been living in harmony for you know, forever. They have brunch every morning. They know that the 99, everyone here knows that the 99 other islanders have blue eyes, right? They know almost everyone on this island has blue eyes, but like, because there is the logical possibility that they might be brown-eyed, nobody has felt the need to leave this island so far. Okay, so one day an explorer arrives on the island, and he doesn't know the rules of this island. He arrives in the middle of brunch. It's like super awkward. He doesn't know what to say to break the ice. And so what he says is, you know, he just blurts it out, you know, at least one of you has blue eyes. Oops. Okay, so you know, this has never happened before. Terrible table manners. The islanders like quickly dispatch of him. They get rid of him, no trace of the body. But, you know, like they can't unhear this, right? Like they've heard it now. At least one person on this island has blue eyes. Now, of course, this does not come to us. This does not come as a surprise to any of them, right? Like they've been having brunch every morning for 100 years, like staring into each other's blue eyes. Each one of them knows already that there's 99 people on this island who have blue eyes, at least. And all they've learned now is that there's at least one person who has blue eyes. They already knew that. And so the question that I want you to think about and discuss on Slack before next class is, what happens? Did this explorer have any effect at all? You know, like does brunch continue to have full attendance like forever, or did something bad happen? Okay. So I'll see you guys next time.